Hi, I'm Yizhou from the University of Auckland. This is a joint work with Miao Qiao from the University of Auckland and Lijun Chang from the University of Sydney. The interconnections among real-world objects can be modeled as a graph. Density, defined as the number of edges divided by the number of nodes, is an important descriptor of a graph. The densest subgraph is a subset of the graph that maximizes the density. It is used in multiple graph analytical tasks. However, as a community detection method, it has a limitation that it can only report one subgraph. To address this problem, a line of research diversifies search results such that, given a node set, the densest subgraph relevant to the query nodes can be reported. One way to diversify the result is to iteratively shrinking the underlying graph by removing the current result, which leads to high computational complexity. Another line of research in 2020 found a way to detect all equally densest subgraphs by finding all minimal subgraphs. However, the result set may degenerate into containing only one subgraph, thus becoming unrelated to the query set. Lastly, locally densest subgraph discovery in 2015 finds the top k disjoint subgraphs from different local regions of the graph. However, the computational cost is still global, which means it is polynomial to the number of nodes and edges. The result set can also degenerate into a single subgraph and become unrelated to the query set. Therefore, given a query set, finding density-based local community search is challenging for the following reasons. Firstly, the result should bias towards the query set without degeneration. Secondly, the new definition of density should have wide real-world applications. Thirdly, the computation should be efficient on even billion-scale graphs. To fulfill these objectives, we derived the problem of anchored densest subgraph search. Given a reference node set R, we define the R subgraph density. It is based on the double of the traditional density, which is the number of edges divided the number of nodes, and then penalized proportionally by the sum of degree of each node in the result set, but not in R. With this definition, an algorithm that finds the densest R subgraph will always bias towards the reference set R. This penalty is derived from our observations of real-world local community search applications. One example is social event planning. A person wants to organize a social event that can establish or enhance his connections. They may have a collection of people that can potentially help establish the connection as the reference set. They post it into a social network and expect a densely connected local community that includes people preferably in R. In finding the densest subgraph around R as a community, it is highly likely that including a celebrity can increase the density of the resulting subgraph. However, if the celebrity is too popular to be within reach of the organizer, recommending them as local community members will become unwise for the system. Another example is the product recommendation based on the co-purchasing network, where each edge represents a co-purchasing of the two items. Given a set of items a customer has visited, we expect the system to recommend items that are most likely to be co-purchased given the visited items. Note that many items may have been co-purchased with popular items such as toilet paper by some users in the past. However, if the visited items are of a special category, for example, comic books of a specific series, then toilet paper does not correlate sufficiently with the visited items. Based on the above use cases, we expect our densest subgraph result to have two-dimensional locality. Inclusion means the result set is biased to R. Centrality means nodes with centralities or degree comparable to the nodes in R. Or in other words, we want nodes with significantly higher centralities are less likely to be included. Lastly, the algorithm needs to be efficient. The natural solution is to integrate the penalty term into the well-known densest subgraph algorithm, whose complexity is quadratic to the number of nodes or edges, which is not acceptable for billion-scale graphs. This is why we designed a local algorithm whose complexity is polynomial and only dependent on the volume of R, which is the first exact density-based local community detection algorithm. To compare their performances in practice, we implemented 2 versions of the global algorithm and then the local algorithm. To compare their practical efficiency, we experimented on 21 rail graphs with 100 queries for each. All graphs contain more than 1 million edges. The largest graph, UK 2007, contains over 100 million nodes and 3.3 billion edges. From the result, we can see that the local algorithm can finish all queries, where the global algorithm failed on some large graphs either due to exceeding the cutoff time or facing an out-of-memory error. For those data graphs that all algorithms can finish the queries, we show the performance gain in terms of time and space for the local algorithm against the global algorithm. In average, the local algorithm improved the time and space consumption by up to 3 orders of magnitudes, and this does not even include those data graphs that the global algorithm can't finish. Some audiences may wonder what kind of property the new densest subgraph algorithm has compared to other local community search algorithms. To answer this question, we made 2 case studies. I will introduce 1 case study, event planning. In this example, we use the DBLP co-author network as the social network. The black node represents an ordinary node we take, who is an author named Yidan Sun, who has 13 co-authors on DBLP. The gray nodes represent the people that can potentially help Yidan Sun to establish their network. The red rectangle SLA represents the result set of our anchored densest subgraph. The blue rectangle SFS represents the result set of the state-of-the-art conductance-based local community detection algorithm in 2019. And the green rectangle SMRW represents the state-of-the-art run-work-based algorithm in 2018. It can be observed that the result produced by our algorithm has the highest density, meaning the high interpersonal connections between these people. Our result is the only one that includes a group of people outside of R, which would be helpful for Yidan Sun to establish new connections. Lastly, the nodes in our result have comparable degrees, making a social event with these attendees comfortable for everyone. This can be contrasted by the SMRW, which includes people with poor connections to other nodes in SMRW, or includes people who have significantly stronger connections to the outside of the result. For example, Malu Castellanos, who might find themselves hard to fit in the social event with people in SMRW. Another case study is Amazon co-purchase network, based on what other items do customers buy after viewing this item. In this example, we choose a Japanese comic book, Oh My Goddess Final Exam, and generate the result for the same 3 algorithms as the previous example. SLA, our algorithm in red, SFS in blue, and SMRW in green. We can see that structure-wise, SLA clearly leads in terms of density, while SFS has the fewest cut edges. Content-wise, however, our algorithm's result contains only and almost all comic books of the same franchise. SFS, however, in addition to our results, also contains DVDs and videos of Oh My Goddess series and other comic book titles. SMRW misses some Oh My Goddess series while including some DVDs. Thus, our result would suit the product recommendation the best, because people who have bought a comic book are likely to have interest in other volumes of the same series. We also did experiments on the same 21 rail graphs, each with 100 random queries, to compare the performance of our algorithm and the other two state-of-the-art algorithms we mentioned. On average, our algorithm's results have a much higher density, have a higher F1 score to the query set, especially when compared with FS, which indicates a better inclusion. Our algorithm is also faster and use less memory by 1 to 2 magnitudes. Lastly, we'll briefly show how our algorithm can have a complexity independent of the whole graph using an iterative process. In this toy example, red nodes are the query set nodes. I will start with introducing the global algorithm. In the global algorithm, all nodes in the graph are used to build a flow network, which can help us to find the R-densest subgraph, which the performance is quadratic to the number of nodes or edges in the whole graph. A local algorithm, however, uses an iterative process that gradually grows the underlying graph we need to build a flow network on. To start an iteration, our algorithm will choose a baseline subgraph that includes only the query nodes and their neighbors in purple. Then we will run the global version of the algorithm with the same query nodes, but only on this subgraph. With that, we can get a result set S1. In the next step, we'll expand the baseline subgraph to also include the neighbors of S1 and run the algorithm again. We repeat this process until the result set ceases to change, at which time we can terminate the algorithm and the result in the last iteration would be the final result, which is identical to the global algorithms. With that, we computed the R-densest subgraph locally around R without visiting the entire graph. To conclude, anchored densest subgraph is the first exact density-based local community detection algorithm. The result set is biased to the query set without degeneration, has wide real-world applications, and is efficient on billion-scale graphs. Thank you.